So we already learned about the wave-field limit, and we know whether we can take that approximation. Einstein's equation in vacuum are going to be this, and the wave equation is going to be given by this expression. So now we're going to assume a solution that is a wave function. So it's a function of the time with some implicit frequency. And the thing to do is to assume something like this with an amplitude and this shape, where obviously this eventually is going to become the wave vector, or the coordinate, what we call it, that we know is the wave vector. So this quantity is like a covariant vector, and is real. And this is a tensor with components that we think they're constant or could be complex. And the equation then can be written this way. And using, let me show what 2 was as this equation, we can write it this way. So this is the result of taking the first derivative. And now taking one more derivative, we're going to get this. And of course, this only going to vanish if, let's do this calculation, essentially the length of this vector is 0. So this means that K is a null vector, is tangent to the world line of a photon, like a Minkowski null vector. And we can see that if this quantity is constant, then this other quantity is constant. So we can write it like this. And now K essentially is going to refer to the spatial components of the coordinates. And Bianchi identities that are automatically satisfied because satisfies Einstein's equations imply this equation here. And that would translate into this, essentially that the K vector is orthogonal to this tensor. So the K0 component is typically called the frequency of the wave, omega, and which means we can write the K vector as omega times a 3-dimensional vector K. And we can parameterize the curve to which this K is tangent in this manner. Lambda is a parameter, L mu is a constant vector, so we can write it in terms of the parameter. And lambda essentially is going to get us the position of a photon traveling along this line. If we calculate K mu x mu, then we can write it this way in terms of the first term and the second term that we used before. And we're going to get the K mu, L mu, because this term is 0, because it's a 0 length, it's going to be constant. So this means that the gravitational wave travels like a photon at the speed of light, and K is the direction of travel. So a natural consequence of Einstein theory of gravity is that gravitational waves travel at the speed of light. The fact that K is null is going to mean that omega squared is essentially equal to the magnitude of the 3-dimensional components of the vector K. And this is referred or called the dispersion relation for the wave. So the phase velocity is going to have to obey this. And the group velocity is going to be the derivative of omega respect to K, equal to 1. So the solution that we obtain to our vacuum Einstein's equation is a wave. It's actually a plane wave. And any general solution of this equation will be a superposition of plane waves. Now, in order to understand better what this wave does and the behavior in the space-time of this wave, it would be good if we can understand what it actually does, or what are the measurable physical parameters of this wave. And so what would an observer see? And we can use the gauge freedom to find further restrictions on our equation. So essentially, if we look for any vector solution of, let me go to equation 3, and that was equation 3. So any vector solution of this wave equation, we're going to find a gauge freedom that we're going to apply. And so another vector, zeta alpha, is going to obey the equation. And essentially, we can play with the parameters to see if somehow we find a more suitable coordinate system where we can understand what's going on. And we're going to choose it this way, where B alpha is a constant and K mu is the same as it was before. And then we're going to get a new wave perturbation that can be written in terms of the old, adding this term with this new vector that we added. And which essentially can be written also this way. And now putting expressly the terms that we assume our zeta has going here, and we can choose B alpha in such a manner that A alpha alpha is 0. This is a choice, and this is the idea of this game, seeing if we can choose coordinate systems that can lead to an easy interpretation of what the wave does. And also, we'll see that for a given for velocity, it's going to be orthogonal, this A alpha alpha. And the other equation essentially is going to give us that is also orthogonal to the vector of the wave propagation. And these two equations, 23 and 24 here, this one and this one, are called the transverse traceless gauge conditions. And typically, every time that you go through the interpretations of a gravitational wave does, you use this transverse traceless gauge condition. And it's traceless because we already saw that adding the elements of the tensor, the contraction of the tensor has 0 trace, and it's transverse because the wave is transversal to the direction of propagation. We're going to see, when I talk about sources tomorrow, that if we give some freedom to the Einstein formulation of general relativity, so we accept some corrections to the theory, we can have perturbations, what are going to be polarizations, that are not necessarily all transverse in the direction of propagation. But I'm going to leave that for tomorrow. So now we're doing classical general relativity, and it's clearly transversal to the direction of propagation. So all the constraints that we use for our H equation they're now the same as H bar, as the original H, and we can write it in this way, because essentially this is what we achieve in this transverse traceless gauge. And what remains now is physically significant. We can choose a velocity such that the velocity can be written like this, so 1 and 0, 0, 0. And the equation then is going to be written in this manner. When we do this, and this is true for all indices, we can essentially orient the space coordinate axis such that the space component is along the z direction, and the x and y plane is perpendicular to that direction, and then we can see the meaning of this transversal perturbation. K is going to become omega 0, 0, omega, A alpha zeta is going to be 0, so essentially all these terms in the amplitude tensor are going to be 0, and only these two terms survive. This guarantees that it's 0 trace, and this makes it symmetric. So there are only two significant parameters. So these are plane waves traveling in the z direction. Now, in order to understand what this wave does, the best tool that we have is studying the deviation of the geodesics. So first, let's take a look at the geodesic equation. So the particle has a velocity u alpha, such that the geodesic equation can be written this way. And let's say that the particle is at rest before the wave arrives. So after an initial arrival time, we're going to get an acceleration that is going to be, in terms of the proper time of the system of reference, be written like this. And this is the terms. And it's essentially, it's going to be 0. So what is the meaning of having 0 acceleration? And the particle is going to remain at rest, because if it was at rest, 0 acceleration is going to remain at rest. So the TT gauge is a system that actually is attached to the objects. As the objects move, distances change, but the system it's not changing because it's mounted, if you want to put it this way, on the wave itself. So that's the main characteristic of the transverse traceless gauge, that you're describing the wave from the point of view of the wave itself. And so the TT gauge is attached to the coordinates. If we have two particles, then one of them is at x0, the other at x epsilon, and of course both we can take it at y and z0. Then the proper distance between these two particles is going to be, the change is going to be given by integrating the square root of the line element. And of course, it's performing this integral, and this is the only surviving term that is of interest, and essentially this is what we're going to get. So in first approximation, what we get is 1 plus 1/2 the amplitude of the wave, that epsilon, which was the distance between the two particles. So the proper distance does change with time. So an important point, and I mentioned, I think it was yesterday or the day before, is the choice of coordinates is extremely important in general relativity. They have little significance per se, but coordinate-dependent quantities, you have to be very careful when you look at them. And one example is this about this situation with the position of a particle. Coordinate-independent numbers are relevant ones, are the ones that in general contain physical information, and one of these is the proper distance, which is what we use to be able to see what was going on. So looking at the equation of the geodesic deviation, which is what are called tidal forces, if we look at two neighboring particles that are moving along geodesics of the gravitational wave, then honestly, I don't even remember now what was this equation from this. It's actually from the previous lesson, but essentially this is the geodesic deviation equation. The deviation is measured by the Riemann tensor. So we can write it in terms of a vector tangent to the geodesic of the space-time that are generated by the passing gravitational wave. And we can write it this way for the U vector that is tangent to geodesics. And we write this in an inertial local frame, not necessarily using the coordinates of the TT gauge. Then we get this expression. And remember that U is the forward velocity of the two particles. So working up to first order in the coordinates, if U is written like this, and the connection vector is written like this, then the previous equation becomes this. This is the only surviving term from the Riemann tensor. And we can try to do an interpretation. So Riemann tensor is gauge invariant, and say that the connecting vector between the two particles gives the proper length of the vector and measure the distance between the two particles. And so we're going to be able to see what's going on here. So we write the components of this equation in the TT gauge, but we know that it's going to be independent on the gauge because that's the reason why we use tensors. And so these are the components of the Riemann tensor, XX, XY, YY, all written in the TT gauge. And this other component is symmetric. So if we had the two particles separated in the x direction by this quantity, then these are the equations that hold. And similarly, we're going to get the same result in the y, the plane perpendicular to the direction of propagation of the wave. And now, if we assume a gravitational wave of this form, one is the term that comes from Minkowski, the one here, but these are the two relevant physical parameters of the wave that we obtain in the TT gauge. So the proper distance between the particles in the xy plane that have positions x0, y0, and x0 plus dx, y0 is going to be given by this. So this is showing that the distance along the x-axis is being stretched and squeezed along the x-axis, while if we look at the two particles which lay at the same value of y, will be stretched and squeezed along the y-axis. So we could think of a ring of particles laying in a plane perpendicular to the z direction, and the ring will be stretched and elongated in an ellipse where the major axis of the ellipse is switching back and forth between the y and x axis and vice versa for the minor one. This is called the plus polarized wave. And what happens with the cross term? Well, we can pick a coordinate system now such that this is the term that survives, and perform a rotation 45 degrees. So then x bar, the new x, is going to be given by this. And by this is just a rotation of coordinates of the system, 45 degrees. And that means that the metric in these new coordinates is going to be given by this expression. And obviously what we're going to see is now the same pattern that we saw before, just displaced 45 degrees. This is called the cross polarization because we have two relevant functions. These are the two possible polarizations of the wave in general relativity. So if any of you is interested in doing exercises, well, this is an interesting exercise. Assume this metric, where now I have specific functions here. And the idea is to calculate the displacement for a photon that is communicating between the two test particles. And another exercise is using this the coordinates for the same metric, do this transformation, and show that a ring of particles perpendicular to the direction of propagation of gravitational wave will be deformed like an ellipse with the passage of the wave. So essentially you're going to get here the ring undergoing the transformation. And you can compute the semi-major and semi-minor axis of the ellipse in terms of the coefficients of the metric. Yes? the effect is real. So if you, the best way to do that is precisely using light. You can use other ways, like looking at the vibration of a resonant bar. But with light, essentially, you're going to measure time travel between the two particles. And if the distance between them is changing, then the time travel got to change. And this is the way you can actually measure the effect. Yes. For some reason, yeah. This one? Huh? The next, the previous one, or the one after this? This one? Mm-hmm. Mm-hmm. Well, they don't need to be infinitesimally close. I'm just taking two particles at a given distance that is commensurate with my capabilities of making an observation. To choose what? Mm-hmm. You're saying choose a curve because you're assuming a curve is space background? Because in this approach, we're assuming a flat. So a line connecting the two. Mm-hmm. Let me see if I understand. You're talking in terms of like a principle of least action. But general relativity, actually, you can formulate in terms of a Lagrangian that obeys the principle of least action, and you know that the geodesics in flat space-time are going to be straight lines. So nature won't choose other paths. The geodesics. Oh, because the two particles, if I understand where you're coming from, that's a good point. Because your two particles are in free fall. So they're not affected, they're totally inertial, or inertial in the GR sense. So if they're accelerated, they both accelerate the same way. So when the wave comes, it's going to affect them in equal way. But they're in free fall. That's the key point, because if they weren't in free fall, then yes. No, all I need to do, well, this is sort of what you're doing with when you look at the deviation of geodesics, you are actually looking at somehow some definition of distance between the geodesics, which is given by the Riemann tensor itself. Well, yeah, but space-time is flat. So when we're doing all this, space-time is flat. And
what you're saying will matter. I mean, when the distance between the particle and the split the mirror becomes comparable to the wavelength.
oh yeah. Oh, actually, this is crucial. Yeah. Tomorrow, actually, I'm gonna look at this and put conditions on this on the wavelength compared to the curvature of space-time. So that's the reason I'm insisting it's you're looking in flat space-time. So you can actually do propagation of gravitational radiation on curved space backgrounds. And tomorrow I'm going to do that.
Yeah, no, the point is actually Lisa will degrade the sensitivity at high frequency, at high frequency, is degraded exactly what you expect. Because the gravitational wave is not on, the wavelength is not short, it's not long.
Yeah.
And so basically this treatment is not correct. So you have to take into account about the averaging of the wavelength along the arc and this effect.
Yeah. Mm-hmm. Well, mm-hmm. But it's a good question. Mm-hmm. So this is just the example because these are PDFs. I cannot show the movies, but you probably saw them. You know, go to Wikipedia, you're going to see them, and the frequency with which they are being stretched and elongated is the frequency of the wave. So I want to talk a little bit about plane waves. Interesting enough, exact solutions, of Einstein's equation representing plane waves can be found. One way of doing this is define what I call null coordinates that can be defined this way, where t is the time-like coordinate and c is just the z direction. And Minkowski metric in these coordinates is going to look like this. And if we look for a solution that represents a plane wave, let's do something like this. You can make it more complicated, but just to make it function only of u is good enough. So add these coefficients, f squared of u and g squared in front of dy. And the idea is to determine f and g solving Einstein's equations. So they're not too complicated to do. These are connection coefficients that survive. These are the Riemann tensor components. And Einstein's equations essentially are the second derivative of f respect to u over f and plus the second derivative of g respect to u over g. And actually, there's a whole family of solutions representing solution for this. You know, one arbitrary way of finding the solutions is picking up a function hu that satisfies these two. So then all we had to do is solve for this. And essentially, the solutions are determined up to two constants of integration. And this family of solutions are called linearly polarized gravitational waves. They represent plane-fronted gravitational waves from sources. And it can be shown that they can be cast in a form that is similar to first order to the general solutions that we found in the weak field limit. So I thought there was some value mentioning this here, but we're not going to work with this. Now, in terms of detecting gravitational waves, so measuring changes in distance with light. Well, we all know that the first efforts started with Joseph Weber, and he worked with resonant bars. And when I finish this part, I'm planning to go over the history of gravitational wave astronomy over the last 60 years, but briefly. But obviously we know that the last 20 years have been dominated by interferometry that has become successful in detecting gravitational waves. So the idea is to look at how effective is an interferometer, just looking at the formulas that we just used. So this is a sketch of an interferometer, and this is a new incarnation of advanced LIGO, and essentially a laser source. It goes through a splitter and moves in two directions at 90 degrees, where two test masses are located 4 kilometers separated one from the other. In actuality, what happens here is these are cavities where the laser beam is made bounce many times to increase the total power circulating here. So the lasers that are being used now are 20 watts, but the idea is to take it eventually, the design sensitivity to about 200 watts. They have a power recycling design that is overly simplified with just this symbol here. And the idea is to be able to go to much higher power, which is difficult to do, to increase actually the powers that is being circulated into the cavities. The reason why high power is desired, well, you have a whole week of instrumentation, but it's essentially because the photon shot noise is reduced. It goes like 1 over the square root of the power. So more power, in principle, you reduce that type of noise in the instrument. So if a gravitational wave comes completely perpendicular to these two test masses, then you're going to see how the distance, well, there are two on each arm, how the distance is changing as we saw it in our calculation before. And so the idea is to calculate how effective is an interferometer. And one way is to look at what's called the transfer function of the interferometer, because it's pretty much related to what we just studied. I thought it was worthwhile presenting this here. So the formula we're going to apply to the calculation of the travel time for a photon in the arms of the interferometer of length L. If we use the metric for the weak field, this is the metric, and we can think that we have a wave with a plus polarization traveling along the z direction that is completely perpendicular to the plane of the interferometer. And then the proper time, travel time for a photon, obviously Diaz equals 0 because it moves along geodesics, non-geodesics. And so this is 0. All we need to do is integrate here, and this is going to give us a ton. So we do an integral in one direction. This is going to be like this. And then we look at the return because it bounces off, and it's going to be given by this expression, and this is the result that we got. And if the frequency of the wave is much smaller than 1, then the metric perturbation can be treated as constant due to the time that we have away from in the detector. Otherwise, it's complicated. So if we assume that h of t is of this form, where this is a frequency of the wave, then we can do the calculations on both arms, and the final result is this. It's expressed in terms of what the cardinal sign function, or sinc, and the theta time, so the time that is traveling within the detector is given by this expression that is rather simple, and the change in phase is given by this other expression. So the idea is to estimate the sensitivity and the response of an interferometer to the passage of the gravitational wave, of course, best possible conditions. Well, now all we need to do is just assume a few numbers, for gravitational wave and look at, plot these functions. And this is what's called the transfer function of the interferometer. And you can see this sensitivity peaks at 100 hertz here. This is in hertz. But of course, I got to warn you to make these calculations simple and easy. I assume 1500. This is a plot, log plot in Mathematica. So I made the arms 1,500 kilometers long, so it's really long. And the wavelength of light is 0.5 micrometers. And but this gives an idea of the possible response of an interferometer and how sensitive it could be at certain frequencies or range of frequencies. The next few slides now. So we saw what is the effect of a gravitational wave. We learned how it could be detected. How is it produced? And that was a matter of debate for almost, I would say, 60, 70 years. So the lowest possible order of radiation is, and this is what we're going to see, it actually has to do with the mass distribution at the quadrupole level. But to see that, let's assume that we are, we need to define these quantities, x prime and x. So x is in the radiation zone, and that means very far from the source. So I actually think that this is way, way much larger than, much longer in size than the source. And using now the wave equation, we can assume that the field point, I'm repeating myself. So the retarded solution, like the one that we can construct in electromagnetism, can be written like this, and this is the energy momentum tensor. And now we use the Laplacian of this, so essentially green function, and we assume that the field point, well, I don't know why I say this so many times. We can replace this by x prime because we are essentially very far. And now we assume that the time dependence is not very strong, and we can replace this by this other quantity. We change our notation, and we can calculate then this quantity. And there are several assumptions that we're making here. One is that the radius is, or the distance is much smaller than the wavelength, that if B is the typical dimension of the system, F and lambda are the frequency of the wavelength and the radiation respectively, then FB divided by C is much smaller than 1, or B times lambda is much smaller than 1. Or equivalently, the typical velocity associated compared to the speed of light is much lower. So the Bianchi conditions make the energy momentum tensor satisfy this equation. We don't need covariant derivatives because we are in this particular treatment far from the source, and we can write the equations this way. And the idea is now to integrate by parts. Integrating by parts, we get this, and working in the same manner, we get this. We can combine now these two equations, and this is what we get. That the integral of the energy momentum tensor is proportional to the second time derivative of the 0,0 component of the energy momentum tensor. If we have slow motion of matter, then essentially T00 is just the energy density and of the matter that is the origin of the gravitational waves. And applying our results to the previous equation, then we can write it this way, because it was T00, we replace it by the density of the system. We can write this integral in terms now of the quadrupole momentum tensor, because after all is the density and the integral of the density happens to be. The quadrupole momentum tensor was pretty much related to the inertia tensor from classical mechanics. So now, if we think in terms of the solving the Laplace equation and solving in terms of a potential and multiple expansion, then we can think in terms of a solution like this. And the solution in multiples are going to be given by these terms: a monopole, a dipole, and a quadrupole. And where this is the monopolar term, the dipolar, and the quadrupolar term. And then we get that essentially the metric perturbation can be written in terms of those quantities. But d tilde k term will not give a zero trace due to what we learned from plane wave solutions. So the final solution essentially is going to be dropping this, and this is the only surviving term. And so monopolar contribution radiation does not appear, and we don't have positive and negative masses. Dipole does not appear because of the conservation of momentum, and the origin of gravitational radiation to lowest order then resides in the acceleration of the quadrupole momentum. Quadrupole tensor of its a mass distribution is 0, so if you have a source that is perfectly spherical and accelerated due to spinning, most stars do, that wouldn't radiate. A different story is there is some departure from sphericity, ellipticity, little tiny mountains. But energy radiated by a gravitational source then can be written in these terms. So this is the origin of the gravitational radiation. The acceleration of the quadrupolar distribution of mass of a source. An example would be a binary system, but also could be some star exploding in a non-symmetrical way. I'm going to come back to this tomorrow when I talk about sources for detection. I think this is the last slide here. And what I wanted, before going into the discussion of sources and trying to touch on a little bit lighter side for this talk, I want to finish the history of gravitational wave detection. I told you up to Feynman and his points of view, and I want to pick up now, like Odelia said, even pretty much at that time that Feynman was claiming that there were no experiments. Weber started performing an experiment. So I want to go from there to the few things that happen in astrophysics who are extremely relevant to gravitational wave detection, and of course talk a little bit about the binary pulsar. So Weber tried to detect gravitational waves with a bar like this. It was suspended. The idea was if a gravitational wave comes and it happens to be of a frequency that somehow is related to the normal modes of vibration of this bar, then the bar would vibrate and you would be able to detect gravitational waves. By the way, this bar is part of an exhibition at the Hanford LIGO laboratory, and you can go and see it. And I had the chance to be there when it was, I guess inaugurated is not the right word, dedicated. Virginia Trimble, who was Joy Ware's wife, was there. And so I think it's only fair to, although Weber made many incorrect claims about the detection of gravitational waves, to recognize that he was a true pioneer in the field, trying very hard at the time that was very hard to detect gravitational waves. So let me show you a few things, because at least for me, it's interesting to see the jargon that we use at the time. This is 1966. And here in the caption for this figure, it says, a schematic diagram of apparatus to measure Fourier transform of the Riemann tensor. Nobody now doing gravitational wave detection data analysis is going to talk in those terms, but that was, well, it was a different time. And one of the things that is worth mentioning about those early years is Weber proved that that very sensitive instruments could be designed, even with the technology of that time, before digital electronics. So one of the things that, at least for me, was most impressive is this is the strongest sensitivity. And his first bar was sensitive to strains of 10 to the minus 16. I think that LIGO now is sensitive to minus 22 to minus 23, so 7 order of magnitude, but it's still pretty impressive. This is one of the most impressive things for me. Slinsky was Weber's student, and this is the second bar. This is the main bar. This second bar is a bar that they were manipulating, so forcing changes in so making the bar vibrate, and this modifying the gravitational field around the bar and trying to detect these changes in the gravitational field with the gravitational wave bar. This is the way they calibrated the bar. So it's a very ingenious way of doing that. Calibration is, as you're going to see next week, is a major issue for detecting gravitational waves, because you don't have a gravitational wave that you can make in the lab, make it happen and see if your detector detects it. So knowing really the sensitivity of the instrument is hard. And as you know, a few years afterwards, he was claiming detection evidence for discovery, particularly after he managed to get 2 bars, one in Maryland and the other in Oregon, separated by 1,000 kilometers, and looking for coincidence of events and doing time shifts, which, by the way, is something that is still done with interferometers. Taking the 2 time series and shifting them in time to look for coincidence. You're going to get a lot of them, but then you're doing the statistics that see how often those coincidences happen and lead you to make a claim of detection. So, well, we all know this are actually, some of these I've taken from, some I took them from the original PRLs, and some are from Harry Collins' in Gravity Shadow. He has a wonderful discussion of Weber's experiments, and he called it the shoulder problem, that essentially all of a sudden he was finding some anomaly, but pretty much everything was white noise and coincidence or Spurrier's noise, and he never really went to sensitivity that could make a detection, although Weber believed that he did. And so the community started just, a few years after that, and a lot of people built bars and didn't make any detection. Even in China, they made bars. Well, and of course, many more were built. This is from Joseph Weber. there was a symposium in honor of 10 Newman in 1981. I was there. And Weber claimed that there was a correlation between neutrino detection and his observations. And well, there was a lot of discussion. They continue even, this is when, 1997. And to a great extent, the whole discussion about the possibilities of discussing, one thing that was discussed a lot was what's called the quantum cross-section, how effective was a bar to detect gravitational waves. And I'm not going to go into the details of this. If any of you is interested, this is a very important paper by Grishuk that makes a thorough analysis of the claims of the people that using bars were saying that the gravitational waves. Well, this is all now, but I think one or two of these bars are still working. Allegro has been decommissioned. That was in Louisiana. Niobe, as far as I know, is not working. But I know that Schoenberg's been moved to ITEP in Sao Paulo, and with plans to really keep working with it. And I don't have a picture of the Schoenberg, or Mario Schoenberg. I personally have a lot of respect for Mario Schoenberg. I think he was a great Brazilian physicist. And make very enormous contributions. This one is a bar made in Holland, and that I think it's similar to the Mario Schoenberg one, right? That's the reason why I put this picture here. Well, so it's still not the end of the history for bars. And but one of the lessons learned, you get to be very careful with the statistics, and that went on into the way LIGO worked, and the LIGO scientists were very careful at analyzing the results. And the scare, the fear for many years to make a claim and going through an experience similar to the one that Weber went. I mentioned the low tide. In going a little bit back to the low tide, in Jean Einstein, a French historian of physics, coined the term. One of the interesting things after the DoD stopped giving money to gravity is that Richard Isaacson went to NSF, and his role was influential in getting LIGO funded. But recapping what was happening in those years of what was called the low tide, from the 30s to the 60s, Carl Jansky finds a source of radio antennas noise, and that was coming from the Milky Way. So this is the beginning of radio astronomy, although it took a while to catch up. And a very important result during the low tide that I think is important to mention. And interesting enough, although the result was important, it wasn't really significant for literature. There almost no citations for this paper from Oppenheimer-Volkoff, showing that essentially what they were showing is by getting this equation that constrains the structure of a spherical symmetric body to a given mass limit, they were showing that star, their first original mass limits were wrong. And so for the neutron stars, not for much, but and that eventually any mass larger than that necessarily will collapse into a black hole. So this was making clear the concept of black holes, although nobody had coined yet the term black hole. This is 1936, I think, and the Tolman-Oppenheimer-Volkoff limit is the upper bound to the mass of cold non-rotating neutron stars, analogous to the Chandrasekhar limit for white dwarf stars. the reason why all this is extremely important, because then clearly there is a path for the evolution of stars, and depending on their mass, some of them are going to become very compact objects, even more compact than white dwarfs, neutron stars, or black holes. 1950s, there was a mysterious radio source that couldn't be identified. They were called quasars. The 60s saw a very fast development of astrophysics. Jocelyn Bell, well, by the way, the quasars were very important because they were very distant source, and they were detected in radio, but they were like point-like sources. That's the reason that they were called quasi-stars, quasars. But they were very far away, and we know nowadays that are at the core of galaxies, and they're related to supermassive black holes. At the time, it wasn't known, but it was starting to pose some interesting questions in terms of the physics that was involved. In 1963, I think it was, Jocelyn Bell and Anthony Hewish discovered the pulsar, the first pulsar. And by the way, they even joke, they call it LGM for Little Green Man. So the first source that was strange because it was pulsating periodically. And in just a little bit later, I think it's Holtz and Taylor discovered the binary pulsar that they eventually studied for a long time, and it was very instrumental in the history of gravitational wave detection. Another important chapter in the saga of modern astrophysics is the Vela Satellites that were launched in the 1970s to monitor compliance with a treaty banning international arms. It was signed between the United States and the Soviet Union. And the Soviets did the same thing because they were, they didn't trust the Americans didn't trust the Soviets. So the Americans put a network of satellites that they launched into space. This one? Huh? This is Kennedy looking at one of the satellites, President Kennedy looking at one of the Vela satellites. Yeah. Yeah, that's right. I think they were finally launched into the 70s, but or late 60s, but yeah. And there were several incarnations, different generations of Vela satellites. So the reason why Vela satellites is so important is because they were very sensitive antennas for X-rays and gamma rays. Actually, originally more for X-rays than gamma rays, and they detected the radiation not coming from Earth, but coming from outer space. That was the first detection of extremely energetic sources. So this is how GRBs were detected, gamma ray bursts. Nowadays, we know they can be classified in essentially two types, depending on how soon they release all the energy content. Those that release, a good fraction of the energy of the burst in less than 2 seconds, and those that release it in more than 2 seconds. Many more than release it in more than 2 seconds. So longer GRBs were found. And nowadays, we know very clearly that the longer GRBs are clearly associated with core collapse of massive stars, so supernovae. And the less than 2 seconds, only very recently has clearly been established that are related to neutron star collisions. Although it's speculated, some indications of it appeared a few years ago, 2013, but it wasn't clear. So it was a mystery for a long time. And another important discovery, I think it's 1971, it discovers signals X1 through X-rays. So it's an X-ray binary, And we're showing that this giant star is losing matter, forming an accretion disk around an extremely compact object. Due to the mass of the object, it's inferred they're going to be a black hole. So the first time that black holes appear to be real. So now, with all this physics that was discovered in the 60s and the 70s, and I'm going to go later, just in a couple of slides, into the Taylor and Hall's binary pulsar. It's good to recap and apply a bit of the formulas that we learned to binary system. This is almost a back of the envelope calculation. I try to be a bit more rigorous tomorrow, but essentially we can write the quadrupolar distribution of a binary system using the quadrupole tensor, and we know that the metric perturbation that will be associated with it is going to be given by 2g over c to the fourth times the second time derivative of the quadrupole momentum, and r is going to be the distance to the source. So actually, the r's are probably, yeah, they're mixed up, sorry. Capital R actually is supposed to be distance to the source, and the small r, like 2 small r, the distance between the two masses. Forgive me for that. So here I'm writing in terms of this, r dot is the distance between, what is called r here is r dot here. So this is xx, yy, and the cross component for the momentum. We assume an orbit for the system, so that the typical radiation is going to be proportional to the orbital frequency of the system. And these are the different components that we get. So we can write now the metric components like this. And the orbital frequency is going to be given by essentially the Keplerian frequency. And with this estimation, then the amplitude, the strain of the wave on Earth, assuming that capital R is the distance to the Earth, is going to be essentially the 10 to the minus 21 in a strain. So the change in distance over the distance. The longer the distance between the two masses you use to detect this guy, then the longer the change, the greater the change. Well, these binary sources exist, and that was what Holtz and Taylor observed. You probably know a lot of this. Let me just mention a few results. It was reported, these results were reported in these results are obviously reported later because they go until 1982, but the system was reported in 1976. But the studies that showed that the orbit was decaying, and was decaying at the rate predicted by general relativity for a system emitting gravitational waves, that was done later. But essentially, we had two neutron stars in mass. Each mass is 1.4 solar masses. The orbital period is 7.5 hours. They are orbiting at 1,000 of the speed of light. The emission of the gravitational radiation causes the two stars to spiral towards each other, getting closer and decreasing the orbital period. The decrease is about 10 microseconds per year, and this is almost 1%, 1 part in 10 to the 14, the one predicted by Einstein's theory. The periastron advances 4.2 degrees per day. Mercury, which is one of the first experimental verifications of the general theory of relativity, Einstein was ecstatic when he realized that he could explain the precession of the perihelion of Mercury, is arc seconds per century. So see how relativistic this system is. And eventually this system is going to coalesce and emit a burst of gravitational waves in about 300 million years. So binary pulsars are very important. they're the ones that essentially lead to the construction of LIGO. And for a lot of the members of the collaboration, the very first candidates that were expected to be detected were binary neutron stars, because nobody knew if there were binary black holes. And of course, a whole bunch of black holes were detected, and only a couple of these guys, and one of them too far away to have counterparts. This binary pulsar is the fastest one ever detected. This one is amazing. It's 16.8 degrees per year, the advance of the periastrum. An important thing was in the field of gamma ray burst was that in 2005, SWIFT detect the first short duration GRB with a very accurate measurement of the position, and to calculate the redshift of the GRB. So that was very significant. So in the history of gravitational waves, a very important role that unfortunately won't be covered in this workshop is numerical relativity, that started in the 50s. It was a lot of people spend almost their careers working in this field. In the late 90s, several people working was called the Grand Challenge Alliance, and there was a project trying to make calculations using as initial data perturbation limits. That was called the Lazarus project. But the full evolution was only achieved in 2006 by two groups, Campanelle, Lousteau, and that were at the time at our institution, and John Baker and Johnson Trela and other people that were in NASA Goddard. And so the end of the history, as you know, the beginning of a new era, it was September 14 when the collision of the two black holes was detected, GWB 150914, was observed with a much filter signal to noise ratio of 24, false alarm rate estimated to be less than 1 event per 200,000 years, so significance greater than 5.1. But it took 100 years to get there. I think today I'm going to finish here and continue tomorrow, if that's okay. You're going to have to speak louder because